All right, we've talked about how water gets into the roots, but how does it get upwards to the leaves? Xylem tubes are pretty small. They're one cell thick in diameter. And so you might think that capillarity or capillary rise in those very small microscopic tubes could account for water movement to the upper leaves of a plant. And in the case of very short plants, that may very well be strong enough. Capillary rise in the xylem of most plants is limited to a height of about 1 meter's worth of rise. And so if we're talking about any kind of tree, that's not nearly a great enough height to get a steady supply of water to the leaves. And so there has to be something else going on. And to explain how the water actually moves, we take into discussing it as what's been called the cohesion tension theory, or just plain old cohesion tension. Water is moving along its gradient. In other words, it's moving from a high concentration soil to a lower concentration in the atmosphere. And through the plant, we call that transpiration. How do the water molecules get up here? Well, diffusion, as we've said before, is a very slow process, and it's not nearly fast enough to account for all the water uptake that most plants do on a weekly basis. So, use the example last time of a mature core plant using in the neighborhood of around 5 gallons of water. That's way more than diffusion alone can account for. And so this is where cohesion tension comes into play. And so we've got two main components of cohesion tension. We've got cohesion, which you should recall means that water sticks to water. The other driving force is the gradient itself. Now, as water evaporates from the surface of a leaf, it makes the jump from an area of high concentration or high water potential to an area of lower water potential out in the air. And so, if we were to depict this in another way, and we can do that by looking at our leaf cross section here, the easiest path for water to get from inside of the leaf to the outside in the atmosphere is through one of these stomatal openings here. And indeed, that's how the water is going to get out and diffuses along its gradient to the low water potential out here in the air. And as it does, these water molecules that are in the vapor form in the interior of the leaf start to get depleted. And the interior leaf humidity or relative humidity is in the neighborhood of 100%. And so on the surfaces of these spongy mesophyll cells, there is liquid water. And so at the interface between the cell surface and the airspace within the leaf, you have evaporation occurring. Now, as one of these water molecules evaporates, another one will move in to take its place because you've created on a very, very small molecular level. Let's say here's a water molecule. Now there's one, and now it is gone. Okay, so in other words, over time, now we have an empty space. Well, if there's another water molecule next to it, now we've got an area of low concentration with an area of high concentration. And so what's going to happen is this one is going to take the place of the one that just left. And so this continues all the way behind it with all the rest of the water molecules. And so they all shift up and take the place of the one that went before them. And the fact that water is cohesive basically means that they all move together. And so because of cohesion forces, water molecules form, we'll say, continuous chains from the inner leaf surfaces cell to cell into the xylem, down into the roots, and out into the soil. So basically what I'm saying is these water molecules form continuous chains through all of these cells and into these xylem tubes. And the chains continue in the xylem tubes, continuous chains down through the xylem. I'm not sure if you can see those dots or not. I'll just do it like this. And out into the soil. Okay, so there's our cohesive chain of water. Okay, and that's due to cohesion. And so that explains the first part of cohesion tension. The second part of cohesion tension is the tension, and the tension is provided by the gradient. The gradient causes transpiration to occur. In other words, water moves from the interior of the leaf to the lower water potential air surrounding the leaf. And so as water molecules evaporate, it applies, we'll say, applies the so-called tension or pull, upward pull, in fact, on the water molecule chains, so to speak. And basically it moves the chains or pulls the chains up one molecule at a time. And so in summary, cohesion tension refers to the fact that water forms continuous chains of molecules from the leaves into the xylem, cell to cell, down the xylem tubes, all the way into the roots and out into the soil. The second part of the story is that transpiration, as these water molecules evaporate, it pulls up the molecule behind them, thus moving the chain up or shifting the chain up one molecule all the way along the chain. And so it, in effect, is pulling the string or pulling the chain of water molecules from the top. And so transpiration applies the pull or the upward pull on the chains. And this is what allows a tree to move water to much greater heights than 1 meter. In fact, some trees can move water up to heights of 300 feet or more.